Please do that. Very good, Humam. Austin, please do this as well. Austin, any answer for the question number 48?
Doing, sir.
No or yes?
Doing, sir.
Okay, please do it first. Very good. You also got the right answer. So the right answer for 48 is B. Ma'am, any answer for question number 49? I couldn't hear you.
Okay.
Any answer? Oh, this question is very easy. It's theoretical. You know, in anti-cancer, you are using cisplatin, and cisplatin is what it is. This B. So it's just a theoretical. We use as an anti-cancer. Please do this. This is you need to solve. Any answer? Any answer for this? Yeah, very easy it is. See, mom, this is D6. That means d orbital has 6 electrons. Now, what you are going to see? Low spin. That means a strong field ligand. That means basically pairing will take place. Pairing will take place. Octahedral. So D2sp3. Now see d orbitals divided into two parts. And since it is octahedral, you are going to divide it like this: T2g and Eg. Yes or no? Now you started filling from here, lower energy 1, 2, 3. Fourth electron will not go into this, but this is 4, 5, 6 because low spin, a strong field ligand. Now, if you are going to calculate CFSC, CFSC will be equal to, as I told you, minus 0.4 into NT2G plus what it will be 0.6 into NEG. And if the answer is in terms of pairing energy, you are going to write XP. That means XP. X is number of paired electron. Now you can see how easy it is. Minus 0.4 into number of electron in T2G. Can you tell me number of electron into T2G? That is equal to 6 plus number of electron in EG. That is equal to 0, right? And how many electrons are paired? How many paired electrons are there? 3. So this will be 3p. This will be 3p. Now you are going to solve it. You will get minus 1.2 minus 1.2, and delta naught is there. I forgot to write delta naught is there. Delta naught plus 3p plus 3p. Since in the option you can see it is given in terms of fraction, so you can easily do this in fraction. 12 by 10, that means it will be minus no what does it mean? How many paired electrons are there? 6 4 z 24 it is, sorry, 6 4 z 2.4. I did it mistake. So it will be 24 by 10, so it becomes minus 12 by 5 delta naught plus 3p. So the answer 3 comes from here, 3 paired electron. So the answer will be this. Yes. AJ, what you have written 0. You were
I'm about to say that 2.4.
6 and 0.4 into 6 is equal to 2.4, right?
Yes.
Minus 2.4. Okay, thank you. Have you got it, Humam and Steen?
Yes.
Okay, please do write it. Let me know when you are done with this.
Yeah, done.
Okay, let's go for factors affecting CFSE, on which crystal field stabilizing energy depends. So, factors affecting crystal field stabilizing energy. Okay, so I'm going to write it down. CFSE. It's just what do we say? Mnemonic CFSE. Just write it like this. The capital letter has meaning. CFSE has, goggles. So GOGLESS. Now see, what does this C means? If you have a ligand which is chelate ligand, that means formation of ring will take place. Let's say this is your M, and we have En, that means ethane 1 comma 2 diamine, right? Ethane 1 comma 2 diamine. So ethane 1 comma 2 diamine is your chelating ligand. Chelating ligand, that means formation of ring will take place in this way, you can see. So what will happen here? Let's take M. So this is your chelation. If there is a ligand that is not forming any ring, that is not a chelating ligand, and a complex compound which is forming chelating ligand. So if there is chelation, that means it will have more CFSE. So that means C stand for chelation. If there is a ligand which is forming chelating ligand it is, then CFSE increases. CFSE increases. There will be some question like they will ask you which one of the following is having high or maximum CFSE. So this is the factor which will come into play. G, here capital G stand for oxidation. G stand for greater oxidation state. Greater oxidation state. If in a complex, if central metal atom has greater oxidation state, that means it will have more CFSE, greater oxidation state of metal. Like for example, you can take if you are going to calculate iron, oxidation state of iron in two complexes, and you are getting Fe+2 and Fe+3. So this Fe+2, sorry, Fe+3 will have more chelate, more CFSE. That means you can see CFSE increases when oxidation state increases. Are you getting my point? This is a symbol for increasing. Is that clear? Now, if you are going for this one, this G, which is also important, that is geometry. Where I will give you which one will have more CFSE. Like if you will see delta naught, delta O, and delta T. Delta O will have more uh, CFSE as compared to delta T. I will give a relation between them, which is very easy. Now for the S here stand for your size. Size more chelation, less small size, small chelation. Sorry, a small CFSE. Are you getting my point? And S is stand for a strong ligand. If there is a strong ligand, then it will be more CFSE. It will have more CFSE. A spectrochemical series. I will give you a spectrochemical series as well right now. Spectrochemical series. Right. In size, we can write size of central metal atom. Everyone knows that 3D, write it in a good way, 4D and 5D. Size increases. If you're going from left to right, size increases, CFSE also increases something. So I think it's clear to all of you. Let me know when you are done with this. You have tomorrow a test for coordination compound complete chapter. It will be there. You can do it. Done. Okay, so in geometry, I needed to tell you for geometry of complex. Geometry of complex. So CFSE of SP, that means a square planar. It's not in our syllabus of CBSE. But still, if they will ask you, it will be like this. Then CFSE, crystal field energy, stabilizing energy of octahedral, greater than crystal field stabilizing energy of tetrahedral. There is a relation between these two. Delta T will be equal to 4 by 9 delta naught. CFSE of octahedral and CFSE of tetrahedral. SP stand for square planar. O stand for octahedral. And here T stand for tetrahedral. I think it's clear to all of you. Are you done with this? Very good. Now see, the next one is your spectrochemical series. So this is a series like electrochemical series you had in terms of standard reduction potential. This is about the in terms of CFSE, what it is. So write with me. Arrangement of ligands in order of increasing CFSE. In order of increasing CFSE. So the lowest so the lowest one is your I minus, then Br minus, then S2O3 minus 2, then comes your Cl minus, NO3 minus, N3 minus S minus 2 F minus. It is in decreasing order, sorry, increasing order. OH minus. Then comes your C2O4 minus 2. C2O4 minus 2. Then comes your H2O2. Then comes your NCS minus. Then comes your EDTA minus. EDTA minus 4. Ethylene diamine tetraacetate. Or EDTA we can write directly. Then PCC. Then NH3. After that, you have EN ethane 1, 2 diamine biphenyl NO2 minus CN minus CO. CO is the strongest carbonyl. So if you're going to check it, you can do like this. Bipyridine it is, not phenyl. This is pyridinium chlorochromate. Or let me know when you're done with this. Wait a minute. We are done with isomerism. We are done with CFT. We are done with VBT, right? We are done with IUPAC as well. Do you know flexidentate ligand? Yes or no? Did I teach you about flexidentate ligand? Chelating ligand we did. And I think flexidentate ligand also I told you, right? No or yes?
No.
Okay, right. A flexidentate ligand. Ligands which have, which can change their denticity. Their denticity. According to situation, they can form, they can act as unidentate or didentate. That is your flexidentate ligand. Like SO3 minus 2 or SO4 minus 2, you can take CO3 minus 2, etc. Are generally act as monodentate. Are generally act as monodentate ligand. But in some compound, they act as bidentate. They act as bidentate. So basically, denticity changes. That type of ligand is known as flexidentate. We can take example CONH3 whole 5 SO4. Here coordination number is equal to 6. That means it is acting as monodentate. And CONH3 whole 4 SO4 Cl. Here it is acting as bidentate. Is that clear? Werner theory we did. En we also did, right? Effective atomic number. Organometallic compound we will study. Let me know when you are done with this. Very good. Now for organometallic compounds. Organometallic compounds. What happens here? Compounds in which carbon atom is directly bonded with less electronegative element. Less electronegative element, or you can say carbon directly connected with metal sometimes. So this is the generalized definition of organometallic compound. For example, element like germanium, antimony, boron, silicon, phosphorus, arsenic. Basically, these are not that carbon or this also forms organometallic compound. OMC I'm going to write organometallic compound. As for example, I'm going to tell you this R is alkyl group which is directly connected to Zn and R. Zinc is a metal which is less electronegative. So this is your dialkyl zinc. Dialkyl zinc, also known as Frankland reagent. Frankland reagent. Another example that we can take is your RMGX that you already know. Mg has less electronegative than carbon, and this is known as alkyl magnesium halide. Alkyl magnesium halide, and this is also known as Grignard reagent. Grignard reagent. Are you getting my point? Yes or no?
Yes.
Please do write it. Let me know when you are done with this. Very good. Now I'm going to give you one more example, and that is, can you tell me this sodium acetate has a formula? I'll write the formula later. And then comes your sodium ethoxide. Sodium mercaptide. Now, if you're going to see, it will be CH3, C double bond O, ONA. And this is your C2H5, ONA. And this is your CH3, SNA. Both of you can tell me whether it is organometallic compound, yes or no? So very simple answer is that these are not organometallic compound. Why? Because you can see sodium is connected with oxygen, not carbon. Are you getting my point? If carbon is connected with a metal directly, that is called organometallic compound. Are you getting my point?
Yes.
Yeah, write it. Because we can write the reason as well. Because in these compounds, matter is not directly attached with carbonate. There will be no assessment test today. Done. Are you done with this?
Yes.
Now, the last topic is your bonding in carbonyls. Bonding in carbonyls. Basically, bonding in carbonyls means carbonyl will be your ligand. So it becomes all the ligand is your carbonyl. So it is your homolaptic. So here I can write only carbonyls are present. Only carbonyls are present. The next I can write is your homolaptic complex. Like for example, I can write NiCO whole 4. Other examples that I can take from NCRT is your with geometry. I can take this. Please write it. Let me know when you are done with this. Are you done with this? Okay. So this is your bonding in carbonyl compounds in which synergic bond forms. What is synergic bond? So I will explain. This is your synergic bond. This is your CO, which is having triple bond. I'm going to write some points and then I will explain. So the first point we can write is the metal carbon bond. In metal carbonyls possess both sigma and pi character. Both sigma and pi character. I'll explain these points right with me. The next point we can write is the metal carbon sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into vacant orbital of the metal. Orbital of metal. The third point I can write is the MC pi bond is formed by the donation of a pair of electrons from filled d orbital of metal into vacant anti-bonding pi star orbital of carbon monoxide CO. So you are going to write all these points. Both of you done with this? Okay. Now see what happens here. Very simple it is. This is carbonyl compound. That means C triple bond O bonding with central metal atom. So coordinate bond forms. That means this carbon will donate one electron, lone pair, and to form coordinate bond. So you can see this is your sigma bond. Now what happens when carbon is donating to M, there will be positive charge and there will be negative charge. So strength of bond increases due to this sharing of electron and due to this positive and negative charge. Electrostatic force of attraction come into play. Now you can see the metal carbon bond in metal carbonyls poses both sigma and pi character. You can see this is your sigma. This one is your sigma. Now, due to this force of attraction, the strong bond, what happens? Metal has electron in d orbital. So this metal will donate electron pair to form a pi bond between this carbonyl and this central metal atom. So what will happen in MC sigma bond is this sigma bond is formed by the donation of electron pair from carbonyl to central metal. Okay, so this is what I have written. MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into vacant d orbital of metal, and MC pi bond is formed by the donation of a pair of electrons from filled d orbital of metal into vacant anti-bonding pi star. Anti-bonding, that means pi star orbital of carbon monoxide, that means this carbonyl group. There will be formation of pi and sigma as well, both together. First sigma and then it will become pi. Is that clear? Okay, now I'm going to give a question. This chapter is completed. Tomorrow you will have a test on this chapter. Please do this. Very good, Umam. What about you, Austin? Very good. Go for 71. So the correct answer is B. You can calculate EAN and say this. Very good, Himam. Austin. Very good, Austin. Are you done with this? C is the wrong answer. This will be your SP3 as you know that. But this is your DSP2 because the strong field ligand here pairing will take place, but from S it will go to D and S will be vacant, so it becomes SP3. This is DSP2. This is your SP3. So the correct answer is B. Is that clear, both of you? Okay, so this is it for today. I will see you in the next class. All the best for your uh, tomorrow's exam, and we are going to start aldehyde ketones in the next class. Which chapter is going on in the in your school? What?
Aldehydes.
Aldehydes. What about you, Humam?
Names.
Same. Can you tell me the topic, which topic is going on, like preparation or in chemical reaction?